So I'm happy to be here, in particular in part of the summer program. I have been here for 2 weeks, so if you are a visitor, I can really sure Vienna is a beautiful city and you are going to have great time here. And I'm going to, my lecture will be, 2 lectures will be part of the lectures on, the total 10 lectures on positive energy theorem. So let me write down the statement, which, let's see. All right, so to make it more precise, the lecture will be on the Riemannian positive mass theorem. Which is due to Schoen-Yau. And I will write down the statement and I will show you the definitions quite precisely of those terms. So we are looking at a Riemannian manifold of dimension n, and G is a Riemannian matrix, and here the dimension n will be greater than 3. And we'll call this Riemannian manifold asymptotically flat. Which I'm going to define precisely, but you can think about, let's just a model of isolated system. So there'll be, everything will going to be like the flat case, which is Euclidean space in our model, because we're talking about just a slice of space-time, right? So it's a Riemannian manifold. And we are shown the scalar curvature is non-negative, which corresponds to the dominant energy condition in this special case. And then the result says, on the conditions, there's a defined ADN mass. Which is a number corresponding to the asymptotic effect metric. That's a number, and the number is going to be non-negative. And the number captures the total mass inside this system. And if mass is 0, that means it has to be the flat model. All right. So there are various definitions, slightly different definitions of asymptotic flat. And in my lectures and also the series lecture on positive mass theorem, we are going to use the Holder space. So we'll define the weighted Holder norm which will just be the Holder norm if you are taking PTE courses. But we are looking at unbounded manifold, so we require some ways to control infinity. So if we have a function, and we can define the weighted norm, k alpha, and with this weight minus q, here k will just be the derivatives, like a usual Holder norm, can be any integers, non-negative integers, and alpha is the Holder exponent, and q is the weight. We are looking at the q be a positive, so that means the minus q will capture the function which really decays to 0 at infinity of some certain rate. But the definition works for any real number, q. And this is defined to be, roughly speaking, we're looking at functions which behaves like a mod x to the power minus q. If you are in the Euclidean space, you are looking at the functions decay to 0, right? But with some rate, minus q. Okay, so let me write a precise definition. So here I define this norm for functions defined outside a ball in Euclidean space. So write a lot bigger or write bigger? Yes. Okay. All right. Yeah, it's hard to see even for me. Let me. Right. So let me write. Next term is really, so the first term really just the, say if you take one more derivative. So if you take no derivative, the function will, so this has to be bounded, right? If we know the function is in this space, it has to be bounded. That means without taking any derivatives, u decays like x to the power minus q, right? It has to be bounded. But if you take one more derivative, the decay rate we require one more higher. Then there's an alpha exponent. All right, so let's use the holder norm, but now we put weights on the holder norm. And this will be k plus, so going to be k plus alpha plus q. All right. So we're not going to use really heavily this norm, but at least you know there's some kind of well-defined function space we are working on for the PDE part.
I'm confused. What is the mean for? You have a mean?
The minimum of x and y. So this is going to be equivalent to your definition. There's another equivalent definition like the one used in your paper.
That's fine. I'm just confused. Why a minimum?
Oh, just because there's a choice of x and y. Right, it's coming from the weighted holder norm on the bounded region. Yeah, so this be the minimum is between just a distance function. Okay. Right.
I'm still confused what this means. So you're just taking the sup of x, y.
Right. So over all possible x and y, and.
But what is the minimum over for? How do you understand this minimum?
The minimum is if you have choice of x and y, right? And then there's a minimum distance between x and y, so you choose that one, right? And then
the minimum of these two numbers.
These two numbers.
Oh, okay. I see.
Yeah.
So this is a number. Okay.
Last
fine.
number,
Okay, good,
right?
Good. Sorry,
Yeah. No, there's always different variables. We blend the boards. Yeah, I should write it larger. Okay, and. So,
the summation should be 0.
Yeah, thank you. Right, summation. Good. All right, so then we are going to use the norm to define to give you rigorous definition, but again, we are not heavily involved in the norm, so everything will be hide under the rug if we talk about the PDE part of this norm. And so let's define the asymptotic flat, and then I'm also going to define the mass. So a manifold being asymptotic flat has several parts. First, the topology. So the topology has to be trivial toward infinity. So the first condition is outside some compact set, the topology is just the exterior Euclidean space. Right? For some compact set K. So people will usually draw this type of illustration, which just means, so here you think about really two-dimensional case. This is surface, a Riemannian manifold. And then there's some compact set K, which you may have really bizarre topology, which people call the wormholes, right? But then there's some compact set which may be very large, such that outside the compact set, it really just has no topology. In the sense, it's just Euclidean, exterior of Euclidean space. So that's the topology part. But then we also require the geometry is asymptotically flat, which means under this diffeomorphism, there's a charge coming from the exterior of Euclidean space, and then we can write down the matrix with respect to this charge will be the Euclidean matrix, Euclidean inner product, plus some lower term. All right. And here Q will just be correspond to the Q there, and for most general case, we require Q to be cannot be too small, has to be greater than this number. But you can just think about Q is an integer. Right. And then this can also be right in the more rigorous in the sense of the weighted Holder norm, because we do require the derivative, the matrix up to the second order and also up to the alpha exponent has to have corresponding decay, so which will be in a sense defined there. And then the last part really is the condition to guarantee the mass is well defined. So we require the scalar curvature to be in this space.
Sorry, so this expression for the metric is for big x's, right?
For big X, that's right, yeah. So this will be for, this order notation will mean when X is large enough, okay? Right, we're going to use the order notation quite often. And so this condition is to guarantee the ADM mass I'm going to write down is well defined, which will be an invariant quantity, does not depend on the asymptotic flat coordinate. And here, just to understand the proof, you don't have to worry about this exponent and decaying, but you can just think about Q is the integer n minus 2, which corresponds to the rate of the Schwarzschild model, which Justin talked about. And you can just think about Q0 is another integer, right? But you just some decay, some good decay. Right. Also, here I will focus on the case of the manifold M is complete, right? But the proof will generalize to the case it has minimum boundary, because less desirable, like the Schwarzschild case, is not a complete manifold with this property, right? But it's actually a manifold with boundary, minimum boundary. And also, you can talk about manifold with multiple ends, right? You have this asymptotic flat end, probably another place you stick out to another asymptotic flat end. That's also okay, the proof will go through. Okay? But if it has boundary, we'll need this to be a compact minima surface. Hypersurface. And let's correspond to the horizon or the boundary of black hole. Right? So now under those conditions, we can define the ADM mass, which is a number correspond to the asymptotic flat metric. So the mass is named after physicist but for sure people call the ADM mass. And let's define using the information of the metric component up to some normalizing constant. For people in the back, can you see it? Okay. All right, so, and this coming from the components here using this charge from Euclidean space. And this common means that the ordinary derivative. And then this, you can think about like the flux integral with respect to the background Euclidean metric. And this is a normal Euclidean normal vector to the sphere. So which are just a quantity, is a quantity defined if you compute each integral over the sphere, coordinate sphere. So there'll be going to be n-1 dimension sphere. And then for each sphere, there's a number, and then you take a limit. And under the asymptotic flat condition, the limit exists. All right. And the positive mass theorem says this number is non-negative under the non-negative scale curvature condition. Yes? The omega n-1 is the volume of the Euclidean n-1 sphere. So which is just a universal, it's constant dependent on n. We are also going to be heavily using the asymptotic flat manifold with special asymptotics code, which just define the harmonically flat. Okay. So let me just remind you the definition. So which will be asymptotic flat of n dimension, but in addition, we assume the metric is actually conformal flat outside compact set. All right? And also we require this conformal factor to have this expansion, which is closely related to a harmonic function. So A is going to be a constant. And if you're using the definition of the ADM mass, A is going to be m/2, which has been discussed in previous lecture, where m is the ADM mass. Okay. So in some sense, the proof of positive mass theory is going to be reduced to asymptotic flat metric of this special type. Okay. So here I'm going to give you an outline of Schoen-Yau's proof to the Riemannian positive mass theorem. So first, I'm going to prove the outline proof for the non-negative part. Because the non-negative part is proved by contradiction, so then one has to argue the rigidity part when m is 0 separately. Okay, so here is suppose this is not true. So this is for the purpose to give a contradiction. Such as there is a matrix with all these assumptions. But mass is negative. All right? And then in the end, it's going to contradict the Gauss-Bonnet theorem in geometry. So the proof is a very beautiful combination of the techniques and ideas from geometry analysis. So the first one, proof relies on the scalar curvature deformation. Suppose there's a matrix with negative mass, and we are going to get another matrix with, from this original one, we are going to get another asymptotic flat matrix with zero scalar curvature. And with special asymptotics harmonically flat. And then again with negative mass. And second is one further deform this matrix. And from this, one can further deform the matrix, but now it's defined on the compact manifold. So there's a closed compact manifold, which is coming from the direct sum of a closed manifold, n-dimensional closed manifold with the torus. So roughly speaking, the idea will be this is asymptotic flat. And then somehow one has to do some magic trick to be able to somehow make it exactly Euclidean outside some compact set. And then you define the quotient space by identifying the opposite sides to make a torus. So the resulting manifold is going to be, this is a torus for identify the Euclidean space. And with this compact part, I call it M1. And they are coming from the kinetic sum, which is really just a way to put manifolds together through an M ball. You remove the M ball there and the other M ball from the torus, and then somehow identify the boundary of the sphere. And moreover, this compact manifold admitting a Riemannian matrix of positive scalar curvature. Right? So that's the part of my lecture. I will talk about the proof of the scalar curvature deformation. And then after that, there's a very, very nice geometric arguments come in, which are working on this compact manifold of admitting a positive scalar curvature using minima surface. So the idea is topology. The torus topology will give you a minima hypersurface by minimizing area of all the hypersurfaces in some class. And if in 3 dimensions, this will contradict the Gauss-Bonnet theorem. So this shows like torus type, like 3-dimensional torus has a minima surface. But then you can apply the Gauss-Bonnet theorem on the two surfaces, somehow which will contradict the existence of ambient matrix of positive scalar curvature. And this construction will work also in slightly higher dimensions through a dimensional reduction argument. So induction on dimension. So in tomorrow, Professor Michael Eckmeyer will talk about this beautiful geometric argument. But then there's a problem in higher dimension because the construction, the mathematical theory for minimal hypersurfaces break down. They are they may have singularities, right? Then the induction will not go straightforward because what if you hit the singularity of minimal hypersurface? So then Professor Rick Shen, in the remaining 6 lectures, will talk about his recent breakthrough with St-Yau, which using so-called, they're defining the argument called minimal key slicing, which somehow handle the singularity. Okay, so my job is to do this part, just a scalar curvature deformation, and also I will prove the rigidity. Because the proof is closely related to the scalar curvature deformation argument. Okay, so that's the outline of my lecture. Questions so far? Can I do that together at the same time? It's okay. All right, so now I will going to give you a proof. And the proof of the scalar curvature deformation relies heavily on conformal deformation. So let me just remind you of the conformal deformation. So if we have a metric which is a conformal deformation of a background matrix G, so U is a function, positive function, and this is a power, which will make the formula really nice. And then you can compute how the scalar curvature relates of these two matrices. So you want to see how the scalar curvature of G bar relates to scalar curvature of G. So there's a formula. Oh, okay. Yeah. So, is that okay?
Yeah,
A little more. Okay. Right, and Cn is a dimensional constant. Since we're talking about asymptotically flat, so our model space is the one with 0 scalar curvature. And so you want to think about, we want to somehow conformal change to make G bar to have 0 scalar curvature. So that makes solving this PDE easier because we don't have to worry about the nonlinear term. We are working on just a linear equation. So really want to look at this linear equation. I want to find a solution such that U satisfy this equation equals 0. Okay. And also U has to be, so U positive, because we want to keep in the class of Riemannian matrix. And then U goes to 1, because we want to look at the class of the asymptotically flat. Right? But somehow, if we want to relate to so-called Dirichlet's problem in PDE, we may be easier just to work on the Dirichlet's boundary condition where U goes to 0. So I can just do that by simple translation. So we will really looking for the solution V, which is u minus 1. And this equation equals 0 will become equivalent to solving this inhomogeneous equation for V. And V. Okay. And so I'm going to write a statement we will need for finding a solution to this type of equation. So that's really the heart of PDE techniques coming inside this theorem. I hope I will have time to prove it, at least sketch the proof. All right, so we are looking for this type of equation, inhomogeneous. Inhomogeneous means the equation, linear equation, equal to something which may not be 0. And so we are looking at, so just to make it more general, we allow the coefficient we denote by F, and the inhomogeneous term was denoted by H. So as in just here later, we will need some condition for F and H in order to solve this equation. Right, so the condition, I'm going to write it down just that you can have a vague idea of what type of equation we can solve. So first, F has to decay to 0 at some rate. Right. And H is going to correspond to the scale curvature, and that's also where the condition we'll need for the asymptotic flat for the scale curvature to be in that particularly weighted space. Right? And moreover, we need F is not too negative. So the negative part of F of this some integral sense has to be small than some universal constant. So where C is this is called the Sobolev constant, which depends only on the matrix and does not depend on anything, the V or H. Right? So where this constant come from the Sobolev inequality, which is the really modification of the Sobolev inequality in Euclidean space, but which just says, so if we have a ball in Rn and V is 0 on the boundary, then there's a relation between the known and the derivative.
Lan, just a
Yes.
question, maybe for the sake of our physicist colleagues, could you remind what the Q spaces are?
The Q space are
The Q norms.
this one.
The LQ, not the C0. LQ.
LP, oh, okay. Yeah, thank you. So LP means the integral known of some power. Right, so, yes. So so you can define this for any P greater than 0. I think most theorem we need is P greater than 1. But just let me put it this way. And this inside the LP space, the Lebesgue integral, the P Lebesgue integral space means so let's just say in Rn. Okay. Yeah.
Are you fixing the dimension because you said F belong to C0?
F belong to C0.
That's
Right. Yeah, it could be Q, but here I just need this to be minus 2. You can put Q there. So Q has nothing depend on dimension. I assume that has condition, right? But general Q defined for any real number. But just in the definition of asymptotic flat, we need that particular dimensional dependent restriction. Right? You can put Q, that's fine. Q is even stronger. Yes, so this is just the setting we need for the PDEs. Yes, thank you. I'm going to write it down. So this means the negative part. Right, so if you think about f is a function, and this is the negative part. But then we flip the sign to make a, I think, in our definition, I think we assume this is, right, so.
This is negative, but not united with positive.
Huh?
This is minus and minus, that's what.
Yeah,
minus and minus.
right, so this is, yeah, sorry. Minus of f. The picture is, so the sign is going to be irrelevant because we're going to have the LP known. You can see that's the absolute value. So you can define your favorite negative part of the function. But here is one definition. It's just say the function f cannot be too negative. Yes? Right, so that's the technical part for the Sobolev inequality. Because if you don't put this condition, then there's no hope to get this bound, right? Because you can just like v to be a constant, and greater than v is 0, and v can be arbitrarily large, right? So one way to fix the normalization in this inequality is to require to be 0 on the boundary. And the other way is to relate it to the average value. Right, so here I define this so here, if you put on the ball, then it's going to be on the ball. But, right, so here it's going to be on the ball. Okay, yeah, thanks. Yeah?
So you also get that v is bigger than -1? Or?
V is bigger than minus.
Yeah, because u is the conformal factor.
Oh, right, yeah. So that's a subtle thing. So V can be negative, right? And right, but 1 plus V is going to, under some condition, going to be positive. Right, so for example, if F, we are going to say that F is non-negative, then you have a strong maxima principle that will guarantee 1 plus V is positive. But then another application we are going to use F is very, very small, right? So then V will be very, very small. So in particular, will be greater than -1.
So this bound on the negative part of f doesn't give you already this, or
right, that's a good point. I don't know. I don't think that will give you generally V is greater than 1, but I have greater than V -1. But I don't think so. But right, okay, all right.
And so your Q naught is the same as above, larger than n, right? The Q naught in this theorem.
That's right. Q naught is
larger than n.
larger than n. All right. Other questions? So how about let me skip the part. I will come back to prove it when I have time. But we're going to talk about two very important applications coming from solving the PDE theorem. So the first one, let me call it corollary. I really wish I have time to talk about proof. Then you will see why do I have to use this Sobolev inequality, the technical thing. Right. But let's talk about application first. So corollary. First one is, let me call it mass decreasing. So this corollary tells you, yes?
You found that the norm should be smaller than 1/6.
Minus.
Sharp or it's
No, it's not sharp. Sorry, it's -2 actually.
And is it sharp or is it just?
It's just convenience.
Okay.
Right. It's not sharp.
So the conclusion of the theorem is that PDE.
Yes, right. Thank you. So the conclusion is under this condition of F and H, there exists a unique solution V solving this equation. And actually there's a more property. So really on this condition of decaying of F and H, you can see V really solve an almost harmonic equation. Right? This is going to go to 0 very fast. So V is going to have harmonic expansion. For some constant A, and then you can find out what A related to the equation. So again, it's just by integration by part of this equation. So they'll be using the trick Justin already talked about in his talk. You integrate the equation. Once you know there's a solution of these asymptotics, and integrate the solution, so then one term you have the Laplace of V, which is a divergence, so you can rewrite as a flux integral at infinity, which will give you, from the expansion, give you the number A up to some constant, and then like equal to the integral of, if you move to the right-hand side, that's integral of this one. So you know what the constant A depends on the equation. So I will talk about two corollary. The first one I wrote down is the mass decreasing. So which says if you are given asymptotic flat metric of non-negative scale curvature and you have a defining a mass, then you can actually decrease the mass in this conformal class. So what you can do is, if you know the scale curvature is not identical to 0, then you can always make a scalar flat, 0 scalar curvature, and the mass is strictly decreasing, and which somehow physically has some interpretation, right? So scale curvature corresponds to the energy from matter field, right? So if you make scalar flat, that means no matter field, and then so that means there's no total energy. The energy has to be. So if you decrease the matter energy, you have to decrease the gravitational energy, right? But it's a very weak, vague relation. But that's the first thing we are going to say. And the second corollary we are going to talk about is, I will call that harmonically flat. It's given a general asymptotic flat metric. You can somehow perturb it. So this time we are going to perturb it outside the conformal class. And then you are going to make it harmonically flat. So we'll simplify the asymptotics. Thank you. All right. It's okay to write on the, or yes, okay. So we should has non-negative scale curvature, but then if it's positive somewhere, then we can conformally change the matrix G it's again asymptotic flat, but this time with 0 scalar curvature, and we're doing in a way the mass of this G bar matrix is strictly less than n of the original one. All right, so I think I will talk about this corollary proof, and then so we will other thing will come back after lunch. It's conformal, right? Yeah, we are not going to use the fact in the proof, but the construction is conformal. All right, so here we really just need to solve. So because we want the G-bar matrix to be 0, so we are going to find U, which is solving the equation from the PDE theorem. Yes. Conformal to G, yes. Okay. So by the PD theorem, there's a solution, right? Because this, if you do the translation trick, u equals 1 plus v, then the equation will be and so you can see that's why we need to assume the condition on the scalar curvature to begin with in the definition of asymptotic flat. So this corresponds to, which we erased already, so this corresponds to H, right? But we need some holder control of H to guarantee there's a solution. All right? So now we know there's a solution, but we need to show it's positive, right? So it's coming from strong maxima principle. Again, another PD result. So strong maxima principle means this type of equation, if in particular the coefficient of the zeroth order term is non-negative, which we have by the assumption here. So if this is greater than 0, then this tells you the minimum of the function has to be positive. All right, so this is a valid conformal factor. So now we just set, and now we're going to give the desired property. We only need to check the mass is really decreasing. Just a remark, this actually, if you allow the scalar curvature to be slightly negative with some control, you can still prove U is positive. But then you have to use a more sophisticated argument, not directly from the strong maxima principle. Okay? And also in the theorem, it gives you expansion of U. So again, integration by part of equation tells you A is and because scalar curvature is non-negative and U is positive and scalar curvature is positive somewhere, so this integral is going to be positive, strictly positive. But we have a minus sign, so this is negative. And then plug in the formula for the ADM mass of the matrix G bar, you'll find out the mass is related by this formula. And A is strictly positive. So, and we are also going to use this corollary in the proof of rigidity. Okay. All right. So I think that's good enough for the first lecture, and we'll return after lunch.